In this video, we'll talk about convolution and mostly about two-dimensional 2D convolution. If you look in Module 3 in the document, the overarching document, and go down, scroll down past what we were doing in the last, past interpolation and zooming to convolution, and we see convolution is a sum of products operation, and then replace the center pixel. So it's a multiply and add, that's a product, and then a sum of products, multiply, add, replace, shift. The algorithm is MARS. I want you to look at, there are a couple of links in here that we'll look at in a moment. I want you to read this and finish it right to the end of the document on convolution. Now, the book talks about this here in section 6.4. We use an asterisk to denote the operation convolution. You know, this is one image convolved with another, and this is the product, the convolution product. One of them is usually an image and the other is a small image that we'll call a mask. This is it mathematically, but it's a little bit cumbersome. I want you not to worry too much about the math, but to read the few paragraphs following that, and especially this diagram here, 6.16. So 6.16 shows what convolution is. We get a mask that is a small image, in this case a 3x3 mask. It's actually a sharpening mask. All masks are odd by odd because they must have a center. Some masks do sharpening, some do blurring, some do other things. This is a sharpening mask. We recognize that because it has a large positive number in the center and small negative or zero numbers surrounding that. So it's a 3x3 sharpening mask that's going to operate on this image. And it's going to move through this image in a raster pattern from the top left to the bottom right. At the moment, it's sitting such that the 9 is above 103. So the mask is sitting in this position here. And what we do is, first of all, take the products or do the multiplication. Multiply 9 by 103 to get 927. Multiply minus 1 by 106 to get minus 106. This one by 79 to get minus 79. And this one by 108 to get minus 108. Multiply the 9 terms here by the 9 terms surrounding this central pixel. So we do the multiply, that is take the products, and then we add all of those products. So we add that to these here, and that will become 130, and then you replace the 103 by 130. And then you move the mask further. It was centered on the 103, you shift it to the right, now it'll be centered on the 70, and you do the product and the sum of products and replace the 70 with what you get. So if you look back to the document and go to this first link, which takes you to a very interesting page, and you should look through this here and read it and try the interactive tutorials. But for the moment, I want to scroll past histogram stretch, which we've talked about, and scroll down to this convolution, which is the same diagram, although colored here. So the 9 multiplies the 103 to give that. We do the other products for all of the terms in the mask, which is sitting at this red position. Do the products, add them up, replace the center pixel, and then shift the mask one position to the right. If we scroll a little bit beyond that, we can pick up on this interactive tutorial. And this shows you an image, small image, 5 by 5, and a mask 3 by 3 sitting on it. And the mask, or kernel as it's sometimes known as, we can use different ones here, but let's go with the sharpening mask for the moment. What we do is we place the mask at top left on top of the image and multiply down the terms. You know, this is a 5 minus 1 minus 1 minus 1. This is a sharpening mask of large or fairly large positive number and then zeros or minus ones. So we position the mask and then do the multiplies. 0 by 40 gives you 0 minus 1 by 68, 5 by 495, and so on. Do those 9 products, and then I'm hitting manual to go to the next stage. Add them all up, do a sum of products, get 259, and replace the 95 with that. And then the next step would be shift the mask across and do the same thing. Multiply, add, replace the pixel, shift the mask, multiply, add, replace the pixel, and then shift the mask, doing this from the top left to the bottom right, the so-called raster pattern. So it moves back and down one, and then you do multiply, add, replace, and that. And we put it on automatic. And that's what it does. It moves across, it moves further, it moves back, across, and produces this new image, which will be sharper than the first image because we've convolved it with a sharpening mask like this here. There are 2 questions you might ask about this result. The first is that it's only 3 by 3 where the image was 5 by 5. Preferably we would want 5 by 5. So you've got to think, how are we going to get the new pixels for these positions? I leave you with that thought. And the second thought is the new image should have values between 0 and 255 for an 8-bit image. But this one has got some negative values and some values above 255. What are we going to do in order to change the values into the range 0 to 255? So I'll leave you with those 2 thoughts. How do we get these pixels, and how do we make the values into the proper range? We can look at another kernel. In the smoothing kernel is very simple. It just multiplies everything by 1. And we can see it just multiplies the 99 by 1, adds them up, replaces the center pixel, shifts. So it's multiply, add, replace, shift. And it works its way through the image. And we have this problem that it isn't going to give us these pixels unless we're a bit clever. And the pixel values are outside of the range. What do we do about that? So 2 problems there for you to think about. The blurring or averaging kernel, this is a smoothing or averaging or blurring kernel, has all positive terms, unlike the sharpening one. These terms are all positive. They don't have to be all ones. I mean, this could be 4 in the center, and these could be 2, say here, and these ones could be 1. Or something similar to that. So you should work with this tutorial and try different kernels and see what's happening. Try it on manual, try it on automatic. We go back here, so we've looked at that and we've tried those things. I want to look at that second link now. If you go to that second link, it takes you to a Wikipedia page which shows you analog convolution. We're doing digital convolution, but it's kind of interesting to look at this here, convolving shapes, analog shapes. If we look at this one, scroll down to get this animation here, it's going to be 2 square pulses moving past. This is the image, this is the mask. It moves across it, it moves through it, only in 1 dimension now, not in 2 dimensions like we've just been looking at previously. And instead of multiplying, it does a kind of integral, but it replaces the values as that mask moves through the image. It's doing a sum of products and replacing and moving on. And the value that it gets depends on how much of this overlaps. And then the central pixel value, the central position is replaced. So this image here gets replaced by this one when it's convolved by another square pulse. So 1 square pulse convolved with another square pulse gives you a triangular shape. That's something we should remember. A square convolved with a square gives you a triangle, and this attempts to show why that should be.